tried hard, but where did we so long? I hope we could, but I won't start over again. Midday street, moral signs, talent disperse in the air. Nobody stops to sit and wait. Your right seems so innocent. Everything makes sense to you. They didn't do me. I didn't compromise for the love. Believe in your words. Way of life, way of life. I heard you say we were on the same street. Way of life, way of my Midday street, moral signs, talent disperse in the air. Nobody stops to sit and wait. Your right seems so innocent. Everything makes sense to you. They didn't do me. I didn't compromise for the love. Believe in your words. Way of life, way of life. I heard you say we were on the same street. Way of life, way of my Or dry winds go by, lonely comes quietly. Or dry winds go by, our sort of space. You need to feel every time. Goodbye to yesterday. Breathe goodbye today. Smiling to tomorrow. No one really belongs. Each time we hope to stay around. I know how you feel beyond your walls. Or dry winds go by, lonely comes quietly. Or dry winds go by, our sort of space. You need to feel every time. Goodbye to yesterday. Breathe goodbye today. Smiling to tomorrow. No one really belongs. Each time we hope to stay around. I know how you feel beyond your walls.
Hi everybody! Welcome back to Chem 161. Just like the music said, it's time to continue with Chapter 4. But we're going to also do a little bit about lab number 5 today. Let's see, what else do we have going on? So quiz number 3 is due this week. It's due on Tuesday. That's the soft deadline. So make sure that you get that in tomorrow. You still have Wednesday to do it if you need to. Quiz number 4 is going to go up pretty soon. We will finish that. We'll definitely finish it by Tuesday, I think. Maya is, of course, here, wants to say hi, and then she ran away, so I don't know what's going on with her. We're going to start with the lab stuff because there's not really too much to talk about for the lab. I'm kind of covering up the chat here, but... So lab number 5 is kind of our summary lab. In a classroom environment, what I would do is I would put down a bottle of wine, not a real bottle of wine, but like synthetic wine that we have prepared. We just put water and then 3 things in there that you were going to test for, and say, tell me what's in this. Good luck, we're all counting on you. And that's it. Like, that's the only instruction you would get. Because this lab is more or less everything that you've done so far. So you can read the instructions to get the gist of what you are going to be doing for each part of the lab. There are 3 parts. The first part is ethanol determination, which we're going to use Beer's law for. Hey, if you recognize what those numbers look like, and you have an idea of what's going on there already, like, you're in great shape. Yeah, you're going to make a graph, and you're going to plot your unknown on the graph. Sorry, actually, that's not right. You're not going to plot your unknowns. You're going to use the equation generated by the unknowns to determine the percent alcohol content in the 2 wines that we have given you, Chardonnay and Riesling. Very important that for part A specifically, preparation of the samples to get these numbers required a dilution by a factor of 5. So just be mindful of that when you are doing the calculation. Like, why is our wine percentage so tiny? I thought wine was like X%. This is why. In part B, there is a titration. This is an acid-base titration. Hey, you did that in the titration lab earlier on in the quarter when we talked about moles. I believe that was lab number 3, which you just turned in. I'm still grading that. You'll get that back soon. But you're basically doing that again. Here's the titration data for Chardonnay Riesling. You're going to determine the molarity of tartaric acid in the sample, given that it is reacting with sodium hydroxide. Now, this time it's a 2-to-1 ratio instead of a 1-to-1 ratio, so just be mindful of that when you do your calculation. The last calculation is SO2, and SO2 is kind of a weird one. So what SO2 is first of all, we add sulfites into wine as a preservative, and when the sulfite in the wine breaks down, it becomes SO2, which is somewhat soluble in the water. And the unit that we use for that is different. So when we express concentration for that, we use these units, milligrams per liter. So you're going to find the mass of sulfite, not sulfite, SO2, that is in the solution based on these titrations. Now, the way that we titrate for SO2 is that we titrate it with iodine. And so what ends up happening is that iodine reacts with SO2 to make stuff. What's important here isn't the stuff. What's important is that the SO2 is reacted, because when the SO2 is no longer present, iodine then reacts with starch that we have put in the solution as a test. So when you add iodine to starch, you get blue. And so what you end up doing when you're titrating this reaction is you add iodine and you swirl it around. You'll see the blue because the iodine finds the starch, but then it finds SO2 and it turns back to colorless. And you just titrate until you get this really deep blue that persists. And what that means is that, oh, I have reacted all the iodine with all of this that was in here, and then any extra created the blue. So all of the I2 that you have added up until that point before the first drop, that turns it deep, deep blue, can be convert it stoichiometrically to SO2. So the reaction that you need is here. It's a 1-to-1 ratio. So for every 1 mole of iodine you dissolve or react, you get 1 mole of SO2 to react with. So that's pretty straightforward. And you're going to do a titration with that. The only difference is that the units here, instead of being in molarity, are... Oh, you know what? I don't think the units of molarity are used for the second one either. We'll go back to that. So the units for this reaction are going to be in milligrams per liter, and I have told you what your answer should be between. So if you get a number that falls outside of this range, then you have a calculation error, and you should post it in Discord or send me an email so I can address it. Going back to lab number 2, you're going to express your units in this different unit down here, mass volume percent. The formula for mass volume percent... What lab did we do mass volume percent? That was the second lab where we did that with, like, sugar. And then just in case you don't remember what that formula is, don't worry about the problems on the left there. We're going to do those in a second. The formula for mass volume percent is mass of whatever you're looking at, and that's got to be in grams, divided by the volume of the solution in milliliters times 100%. So in other words, since this lab is looking at tartaric acid, you're going to find the mass of the tartaric acid and divide by the volume of wine that was used. And then times that by 100%. And you should get an acidity. It should be less than 1, I think. I want to say it's less than 1%. So like 0.1 or 0.2 or 0.5 or something like that. All right, so those are the ranges for the 3 numbers. In fact, we'll just write them down here. So ethanol. So we'll go expected answers. Just in case, like, this isn't in the lab somewhere. So for ethanol, you should get a percentage of ethanol between 1 and 15. Obviously, you can't go over 100% ethanol because that's impossible. And if you got a really tiny number for ethanol, like 0.2%, that's wrong because you didn't multiply by 100%. So just be mindful of that, that's a thing that you need to do, is that 100% at the end is going to be important. For tartaric acid, should be between 0 and 1%. And then for SO2, in milligrams per liter, should be between 20 and 40. This is mass volume percent. All right, so your answers are somewhere in there, and you're going to be graded on your calculations and how close you get to the correct answers. Because this is a worksheet, this lab is super easy now. But what it does take is time. Not why I was playing that song at the start. But it will take a little while to wade through the calculations, and there are a lot of them. So the worksheet is it's very calculation intensive, but conceptually it's not difficult because you've done all of these things before. So again, this would be the Beerslaw lab. This is the titration. Actually, I think that was lab number 2. And then this is also a titration with different units. That's really all I got. So if you have any questions about that, let me know, and I'll be happy to address them. Okay. So with that out of the way, what I'm going to do is I'm going to then direct you over to these questions. Boop. This is where we left. Oops. I forgot that I had put that there. We don't need that. Hi, yeah. So when nobody talks during the first 10 minutes, I'm always like, are there actually people here? I just checked. There's 8 people watching, which is actually a lot. For week 10, a third of the class showing up is pretty good, actually. So what I want you to do, just as our warm up here. So I forget which one I did. I already drew IF5, I believe. So I want you to apply the rules for Lewis structures to drawing these structures, and then I'm going to go over the answers, and we'll do the 5-step plan for the remaining 5 that we haven't done yet. Okay. So draw these Lewis structures. If you've already drawn them as an exercise of the weekend, then you're all set. But I'll give you 5 minutes to do this, and then we'll do these, and then we're going to talk about how we can make our structures better. So the whole point of the next section is going to be how do we take Lewis structures and make sure we're getting what the molecule actually is out of them. And there's a few things we can do. So see you in a bit. All right, one more minute. We'll go over the answers. Say hi. What's the answer to number 3? Okay. That's wrong, but... Alright. Maya's here giving you guys wrong answers. Alright, let's go over the answers here. I gotta click over here. And... Oh, I moved the wrong thing. Hold on. There we go. That's the one I want to move. Actually, let me just do that. You can't see what I'm doing. I'm fighting with the interface here. Yeah, Maya has little tiny meows, except when she really wants attention. Then they're like really, really, really long meows. Like she'll sit there and go, meow. Like you've seen that meme, little tiny black cat do. She does that, except not as cute because she's not tiny. Yeah, you're still cute, just not as cute as the kitten on the meme. Oh, every cat's dream to be like the kitten on the meme. Alright, so you can't see that because I drew behind the thing. There we go. But yeah, she has this tiny little chirp when she's happy. Alright, so what we're going to do is we're going to count its valence electrons, and by now you should be able to count valence electrons pretty quickly. And this 3 here, we have to add 3 electrons. So this should be 24, 29, 32. And we're going to create our framework here. So that was 2, 4, 6, 8. So I'm going to deduct 8 electrons. And then go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Wait a second. Why the heck is this in the exceeds the octet rule chapter if it doesn't exceed the octet rule? Well, what we're going to find out is that this is the answer for now, but in the next section, we're going to learn that you just take one of these and go boop, and that's actually the best answer. Why is that the best answer? We'll talk about it. So this is good for now. We got xenon difluoride. Wait a second. What the heck? Xenon? Xenon can make bonds with stuff? Well, it turns out if you have something that's electronegative enough and something that's big enough, those two will react. And so fluorine is super electronegative, so it'll pull electrons away from almost anything. And xenon is big enough that those electrons that are extremely far away can react with xenon. So xenon's kind of the noble gas that sneaks out with the riffraff being fluorine. And actually makes some interesting compounds. So there are Xe based compounds out there. So there's fluorine and oxygen xenon compounds. All right, so we'll go XeFF. I didn't even add these together. I should do that. So that was 4. And I'm going to go 2, 4, 6, 8, 10, 12. And then I have 6 left over. Those got to go on the central atom. So 1, 2, 3, 4, 5, 6. And this is the correct structure. Now, it looks really weird to have those extra electrons on the central atom there for xenon, especially because it's a noble gas. Excuse me. But that's what the rules tell us to do. Do all the octets on the outside and then just dump all the remaining electrons on the inner atom, and you'll get the right structure. So for xenon, even though we kind of exceeded 4 sides, you just start putting them in places so it looks like there are more sides. So you can see that it kind of looks like there's 5 sides. The whole point of today's lecture, after we finish Lewis structures in the first hour, is that we're going to be talking about geometry. And so you'll see what a 5-sided three-dimensional shape eventually looks like. It looks kind of like this, just as a... So that triangle is a plane, and there will be something at each corner. And then there will be something here and here. So that's what a 5-direction structure looks like. And we'll get to that. We'll get to what that means. I'll draw a better picture, for one. I should make these look like capitalized. There we go. So iodine tetrafluoride ion. So I get 7 for each fluorine and for each iodine, and then this minus gives me an extra one. So this is 36 electrons I get to work with. So I'm just going to connect everything. So doot, 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 doot. Since I don't know what the shape will look like until it's done. That used up 8 electrons. And then we'll just go around here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Everyone gets an octet. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So 24 from 28 would be 4 are left. So I got to put the remaining 4 on the central atom, so I'm just going to do this. And if you're curious what shape that has, well, that's just like having a square. Kind of like our triangle thing was up there, right? All right, let's do SCl6 and then ASF6. I'm going to run a space, though, so I'm going to go up here. Oh, Maya is already back. Maya, I'm working. She doesn't care. So each chlorine is 7. There are 6 of them, and then plus this sulfur is 48. Like, I can't record what sound she's making right now, but... Can you do it? See, she's already sounds much happier because someone's paying attention to her. But when somebody isn't paying attention to her, she starts whining. Too many hugs. Don't hug your cat too much, or else they will become whiny like Maya. So you can kind of see I'm trying to model this shape down here. So there's my square, and then there's the front and the back thing. So 2, 4, 6, 8, 10, 12. So 6 bonds is 12 electrons. 48 minus 12 is 36. And I'm just going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. I kind of messed up there. 24, 26, 28, 30, 32, 34, 36. Look at that. Use them all. There's the structure. Something I just realized I forgot to do down here. Forgot to do this thing. So just be mindful of that. And then for ASF6 minus, you're going to notice like, oh, look at the same number of electrons. Who could have imagined this? 42, 47, 48. And so, interestingly enough, if you get the same number of electrons, you get the same structure. So here we had 48, and down here we have 48. You're going to get the exact same thing. Because all we care about, really, are the number of electrons that'll be in the structure, right? So that was 6, and then the remaining 36 would just go around. That one didn't really turn out to look like a pair there. I'm kind of crammed in the corner anyway, but this will look exactly the same as SCl6, with the one difference is that it's an ion, and so we got to do that. All right, so those are all of our Lewis structures that follow the rules that we talked about last week. So now that we got that down, we can start modifying this with a new concept called formal charge. And that's what we're going to do. All right, so before we start formal charge and resonance structures, it's really important to mention that these are models. And that whenever we use a model, just like a Lewis structure is a model, these things are also models. Models aren't perfect. Models model what it is that we're looking at. So formal charge is not a real thing. It doesn't exist. We're going to make it up, though, so that it helps us get the structures that match up with what we observe doing experiments. And then resonance structures, again, don't exist. But the information that we are using in this practice helps us understand what a molecule really looks like. Okay, so at the start, remember that what we're doing here is basically just fictional, but it does help. Kind of like the economy. Like, the economy is fictional. It doesn't exist, right? But we use it to help govern society and make money have value, right? Because we have to give it value. All right. Now, when you draw a Lewis structure, you may have gotten in a situation where you thought to yourself, well, wait a second, I have choices. I can make a double bond in multiple places, but I get a different result depending on what I do. So, for example, if I did CO2 here, what's stopping me from saying, oh, I'm just going to put all the double bonds on the left side, make a triple bond, and then have a single bond on the right side? And the answer is, well, if we check octets here, and I go 1, 2, 3, 4, 5, 6, 7, 8, that's an octet. Each of these bonds is 2, that's an octet. And then over here is the same on the left, 1, 2, 3, 4, 5, 6, 7, 8. That's an octet. So that satisfies the octet rule. That's fine. But if I do the same thing over here, 2, 4, 6, 8, I notice that everything also satisfies the octet rule. So every atom checks out and has followed all the rules up until this point. How the heck do you differentiate between them? And the answer is we're going to employ a strategy called formal charge. And the way that you calculate formal charge is the following. I'm going to abbreviate it FC. We're going to look at the number of valence electrons an atom brings with it at the start. So, like, carbon would be 4, or oxygen would be 6. That's what they started with. And then we're going to go minus. We're going to look at the number of, I should probably write valence electrons because we're dealing with valence electrons here. We're going to look at the number of valence electrons that the atom has at the end of the structure that you have drawn. Now, we're going to import a caveat here. And this is different from counting for octets. Anytime you have a bond, we're going to count it as 1 electron. Because the electrons are shared, that atom doesn't own all of them. So we're counting the actual number of electrons around each atom and not just counting for octets for stability. Okay? So let's do some examples here. So I'm going to pick this atom over here, this carbon, or I'm sorry, this oxygen right here. How many valence electrons did it start with? Well, all oxygens start with 6, because they're in group 6A. Then I'm going to go minus how many electrons are present. I'm going to go 1, 2, 3, 4, and then each bond is only worth 1 now, because I'm going to split the bond equally between them. 5, 6. So this oxygen has a formal charge of 0. Now I'm going to come over here and do this for this oxygen. This oxygen starts with 6 because all oxygen does, and then I'm going to count electrons. 1, 2, 3, 4, 5, 6, 7. So that oxygen has a formal charge of -1. This oxygen over here is the same as this one, so I'm just going to write its formal charge here. This oxygen right here, 1, 2, 3, 4, 5, has a formal charge of +1. Now, what do formal charges care about in these structures? Well, writing a formal charge is implying that the charge is gathered on the side with the negative formal charge and has been pulled away from the side with the positive formal charge. Now, looking at the nature of this bond, would it really make much sense for this to happen? Oxygen is very electronegative, but so is this other oxygen over here. So they would be pulling equally. Why would this oxygen pull harder to get the -1 formal charge, and this one just get shafted and get the +1? That doesn't really make sense, right? Because all oxygens are equivalent. They have the same Z effective, they have the same size. They should pull with the same strength because they're in symmetrical conditions around this carbon. So this structure on the left here has some issues that it's hard to resolve. And the issues come up from formal charge. So if I get a distribution of charge in a molecule where it doesn't really make sense, and that's going to be almost all the molecules we look at because they're all going to be symmetric in some way, then we disqualify that structure. So I would say that the structure on the right here is a bad Lewis structure for this and is not the best one. The one on the right here is the best one because all the formal charges are 0 all the way throughout. So when you're drawing a Lewis structure, your goal is to have your formal charges be as tiny as possible. If you create formal charges, then you're moving your bonds around in a way that's separating electron density kind of arbitrarily. And we don't want to be arbitrary with our Lewis structures because they're going to be just the average of whatever the lowest possible energy result is, right? All right. So up above here, I've calculated the formal charges for all the atoms here. And remember that our takeaway here is that the closer you get to 0, the better. And so because the left structure has all zeros, it's the better structure. And for our purposes, when we say better structure, we mean it's the correct structure. Now, when you follow the rules for drawing Lewis structures for everything, in some cases you will get to a molecule that has odd formal charges, and you might think to yourself, well, wait, maybe I should continue making double bonds to the central atom to see if I can change some of these numbers. And that's where PO4 is going to come in. So let's go back to this structure that we had up here. If I could get it to stay on the screen here, there we go. And we'll just do this. That's not what I meant to do. So what we're going to do is we'll go like this. Hop, boop, boop, boop. All right. So he lives there now. And now what we're going to do is we're going to calculate the formal charge for the structure. I'm going to clear this. Don't worry about that, whatever the hell is going on there, because I'm just going to do that and it'll go away. And so what I'm going to do is I'm going to circle an atom. And we're going to calculate the formal charge of this. So what is the formal charge of this oxygen by your calculation? Type in your answer in the chat. And that's going to be the same calculation for all of these, because they're all identical, right? They all have the same circumstances around them, 3 electron pairs and a bond. So tell me what the formal charge is for that oxygen, and then calculate the formal charge for phosphorus here in the center. And type your answers in the chat once you got them. We'll go over it together in just a bit. -1 for which one? Or which atom? P or O? All right, cool. Okay, let's do the calculation. So oxygen starts with 6, and its current state, it has 1, 2, 3, 4, 5, 6, 7 electrons around it. So all these oxygens are going to have a formal charge of -1. Then, when we do this for phosphorus, phosphorus starts with 5, but it only currently has 4 because 1 for each bond that's around it. All right, have we separated out charge here? I mean, we kind of have, right? We have separated out a charge from all the oxygens and this phosphorus in the middle. Now, if I can reduce those formal charges even slightly, I will get a better Lewis structure. So what we could do to reduce these formal charges is I could draw the Lewis structure like this. So I'm going to put my O's around here. We're going to draw it as normal, just to have a copy of it here. So here's my structure. I'm going to erase one of these pairs and do that. And now we'll check formal charges. These are still -1 because I haven't changed them. But this top one right here now becomes 0. And this phosphorus down here also becomes 0. Now, for these structures, we just said now we have to kind of check against what makes sense and what doesn't, right? Oxygen's really electronegative. Would it pull electrons away from something that's electropositive? Yes, but not in equivalent directions, right? So why does one of these get sort of shafted? And so you might think, well, wait a second, the left structure is more symmetrical. Maybe phosphorus just gets screwed out of electrons. I have -1s everywhere, and there's just a +1 in the center. And that's actually a pretty good argument. However, we don't want to have something that is tons of charges everywhere. And so in reality, this is going to require us to get to the resonance structures. Turns out that neither of these actually represents the best answer. Believe it or not. The best answer is sort of the average between them. But for our purposes, when we draw a Lewis structure using formal charges, we're going to impart the following recommendation. And that recommendation is to minimize formal charge whenever possible. So on the basis of minimums, this structure is better because there are more zeros in it. Now, can you get everything to be 0? Turns out that that's impossible. And the reason that it's impossible is because the overall charge of the structure is going to have a -3 to it because it's phosphate, right? So we got to do this. But if you look at the sum of all the formal charges, so here's 4 negative ones and a positive one. The sum of the formal charges will equal the charge of the ion. Whether it's polyatomic or not. So if you look at your formal charges and you add them all together and it doesn't total up the sum of the ion, or 0 in the case of if it's just a compound that's neutral, you've made a calculation error. So just be mindful of that. But if you were asked, choose the best Lewis structure, pick the one that has the minimum formal charges everywhere. Now, let's suppose that I wanted to, I don't know, we learned that phosphorus could accept multiple bonds from stuff, so I'm just going to go crazy and start bonding it as many times as I can. And this is where that intuition part of the question comes in again, where we could say, okay, well, this is 0, this one's 0, this is -1, this is -1, and this is also -1. So overall, they add up to -3, so that checks out. But now the issue here is that I have something that is not as electronegative with a negative formal charge, whereas the oxygens don't. So is this a good structure? Well, this calls it into question, right? So with formal charges, there is a lot of sort of weighing, I guess you could say, about like what's the best answer. And when in doubt, we're going to default to this. Try and get your numbers as small as possible, but put them in places where it makes sense for them to go. And if you have an issue with a structure and you're like, well, that's weird, this is not as electronegative, why would it have a charge? Or this has fluorine in it, why am I making it something that isn't -1 or 0? Those are all very good circumstances to consider. All right, so we'll go to the next example and we'll see this in action here. So here are two scenarios that I could draw for SEN. So the overall charge is going to be -1 because it's right there. I didn't put the brackets in yet because we needed the space to work with. What I want you to do is tell me which structure is right, left or right. I guess I should say which structure is correct, the left structure or the right structure. And do that by writing out all the formal charges. So Now, you might end up realizing that, wait a second, I just get the same thing mirrored here. What's the correct answer? And so then read the little blurb at the bottom here and see if that matches up with what we were talking about before. And while you do that, you can listen to this really sad cat. Yep, that's what I deal with every day. All right, who's willing to stake a claim? Which Lewis structure is the better one? Let's draw out all the formal charges. So first, let's look at carbon in the center. Carbon is just 4 minus 4. So both of these carbons are going to be 0. Let's look at nitrogen on the left here. So nitrogen starts with 5. And it ended with 6. So its formal charge is -1. How about sulfur over here? Sulfur started with 6 and ended with 6. So its formal charge is 0. That looks kind of like a 6. Let me fix that. All right. Now go to the right side. Nitrogen has 0. Over here, sulfur has -1. All right, so our structures have our -1, which checks out because our, oops, I didn't mean to mark there. Our ion has a -1 charge. But where should that -1 be? Should it be on nitrogen or sulfur? And the answer is, well, nitrogen's more electronegative than sulfur, so it should be on the nitrogen. So the left structure is the better structure. So formal charges are basically like you're making a case for which is the best structure. And the points that we have come up with so far are minimize formal charges, try and get as many zeros as you can, and assign formal charges in situations that they match up with what we would think the electronegativity would do. Some atoms naturally want more electrons towards them, and other atoms naturally are disinclined to have electrons. They don't really care. Some atoms will just do whatever. Like carbon in the middle is just kind of stuck here. It doesn't know what to do. So give the negative formal charges to the more electronegative atoms, and that will generate the correct structure. All right. And this slide just says, yeah, formal charges don't exist. Don't worry about it. So we just talked about this. All right. So we've already done this question down here. So now what I want you to do is I want you to draw as many different variations of Lewis structures for these three things, and then pick the best one. Because there's going to be all sorts of ways to arrange electrons around them. Choose the best one that gives you as low formal charges as you can. Now remember, you do have to satisfy the octet rule. We got to have a stable molecule to start with. So if you get something that has 0 formal charges, but everything doesn't have an octet, then the molecule will just be reactive. And so that structure won't be stable. All right, so try it for these 3 molecules. You don't have to do PR4. We already did it. And we'll go over the answer in just a second. All right, one more minute. We'll go over the answers here. By the way, she's still doing it. You know, I might have to set up a thing where the chat like votes to hit a button, and when they hit a button because they're tired of you, you get the squared model. Oh, the joys of living with a cat that is spoiled. You'd think that as far as we are into the pandemic, that my cat would realize, yeah, I work at home now. But I guess not. All right, so let's draw a Lewis structure for NO plus here. And so the number of electrons that we have is 5 plus the 6, but I have to deduct 1 for that. Positive charge there. So my structure should have 10 electrons, and I'm just going to stick these together, so that's going to be the first 2. And I'm going to follow the rules. I'm going to put outer atoms first, so 2, 4, 6, 8. Alright, it's time to squirt bottle you. Go away. And I don't have an octet on nitrogen here. Excuse me. So what I'm going to have to do is I'm going to have to move electrons into this bond here. So still don't have an octet. Now I have an octet. So this is really the only way that I can make an octet occur. Because if I move the electrons anywhere else, somebody's not going to have an octet. Now, when we get into this situation, we end up with a weird number that we get as a result. So for nitrogen here, nitrogen starts with 5 and ends with 5 here. So this is a 0. But over here for oxygen, oxygen starts with 6 but still only has 5. And I mean, we literally just talked about, well, what can I do? I don't want this positive on this oxygen side, right? It's the more electronegative atom. But is there an alternative that satisfies the octet rule? And the answer is no, there kind of isn't, right? Oxygen's just kind of screwed in this case. So this is actually the correct structure by virtue of there being no other structure that satisfies the octet rule. Remember, you got to satisfy the octet rule first before we can even get to formal charges. All right, SO3, we have all sorts of options here. We're going to try and find the best one. So 6 plus 3 times 6 should be 24. So that would cost me 6, so I have 18 left. And then I go 2, 4, 6, 8, 10, 12, 14, 16, 18. So you start with the 6 electrons for oxygen because it's the more electronegative atom, and it's the outer atom. But even though the end result is that you end up with a positive over there, you still follow the rules the same way. If you put them on nitrogen, you'd end up making bonds over to oxygen anyway. You'd actually get the same thing, it turns out. Here's our structure for SO3. I don't have an octet for sulfur, so what I need to do is I need to do something like this. So now I have an octet, so we can work from here. So if I do formal charges, I would get 0, -1, -1, and then +2. Ew. That's gross. Can I alleviate this structure? Well, if I move some of these electrons in here, So let's reproduce the structure, but with just this change here. And so now when I've done that, this is still 0. This has become 0. This is still -1. And this would be, sulfur starts with 6. Over here it only had 4. Over here it now has 5. So it's getting better. Can I improve it further? Yeah, you totally can. So here's what we had before. There is my single bond. I'm going to just turn it into a double bond. And now when we do formal charges, you get 0, 0, 0, and 0. So what's the best structure? This one. Believe it or not. Now, why am I adding more electrons? I already have an octet. Remember that atoms that are beyond the third row can have more than an octet. And so if we can stabilize our formal charges by just making more double bonds, then let's do that. The only requirement that we have to hit is you have to hit an octet. You can go past the octet for the central atom, but you have to at least have an octet for everything. All right, finally down here we got O3. O3 has just 3 times 6 electrons. So we're going to just put this together like that. So that's 4 that I used. So 2, 4, 6, 8, 10, 12. So there's my outer atoms. They're taken care of. I'm going to put the remaining 2 on the central atom. And then I notice, oh, I don't have an octet yet, so I need to make an octet. So I'm going to go like this and like that. All right, so everything has an octet. Let's do formal charges. So oxygen on the left, oxygen on the right, oxygen in the middle. That's weird. Is there a better structure? Well, what if I put the double bond on the other side? Or maybe made a triple bond. So if I did this, then the issue becomes this is not allowed. So I cannot exceed the octet rule for a period 2 element. So this structure is no good. What if I tried to put the double bond on the other side? Well, then all I do is move the formal charges. Oops, wrong color. To the opposite sides that they're on, right? So that doesn't solve the issue. Now there is one more structure that actually solves everything and ironically doesn't happen. And we're going to talk about why it doesn't happen in the next section. We're going to draw it right now. So if I did this instead, and instead of making a double bond, what if I just did that? And then I'm like, okay, now I'll just put 2 electrons on each of these sides. Are there 18 electrons? 2, 4, 6, 8, 10, 12, bond, 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 18. Yeah, shouldn't this work? I calculate all the formal charges and I get 0, 0, 0. Shouldn't ozone just be this little triangle guy that floats around? And the answer is no, it totally doesn't happen. And there's a very specific reason for that. And it has to do with how tight this angle is. Those electrons in those bonds repel. And they prohibit that structure from forming. Otherwise, it'd be a great structure. It satisfies the octet rule. It satisfies all the formal charges. But we haven't even talked about geometry yet, so we'll get to geometry at the second hour of the lecture. All right, so what we want to look at, though, is for this, here were the answers that we came up with. And we can't really distinguish between these two because they're essentially equivalent, right? It's just whether I put the double bond on the left or the right. And so this is a special case that we're going to talk about when we come back from our break. And so this is what is known as resonance structures. Sometimes when you draw your Lewis structures, you get equivalent results. Whereas it's just symmetry is what dictates the difference between the structures. And you just rotate the whole thing around. But in reality, rotation is not that simple. And so what we're going to examine when we come back from the break here is what governs whether a resonance structure exists and what's the actual structure of a molecule. Because you can't just have a double bond in both places, right? That wouldn't make sense. That would break the octet rule. So we'll talk about that after the break. And I'll see you for that. Let me go get more Persona music. We're doing Persona this week, so that just basically means J-pop all the time. So enjoy.
I never felt like down. I never felt like down. But they're still with me. Down. You gotta turn up down. I never felt like down. I never felt like down. But they're still with me. Down. You gotta turn up down. I never felt like down. I never felt like down. But they're still with me. Down. You gotta turn up down. I never felt like down. I never felt like down. But they're still with me.
covers all society. Damn right, mom is not here, gonna fight all night. Right here, shadow 10 o'clock direction. Seize the moment, destroy the nation. You run slow motion, give me motivation. Breathe out now, and then on the rival. Round up around, spit out all over. Rhyme like a rolling stone, come in the crowd. Watch out the moon, that this too loud. This was this sound and bombs whole ground. Surround up, don't ease your pace, cause enemies brutal. Moment of truth, there ain't no truth. You're the only one world, one law. But the battle goes on, shadows all mass destruction.
Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby.
Battlegrounds right here. It's a man's world. Gotta get ready for this right here. Hey yo. Here's a wake, anger breathes out, face reality. Never be charity. The enemy, your buddy, covers all society. Damn right, mom is not here, gonna fight all night. Right here, shadow 10 o'clock direction. Seize the moment, destroy the nation. You run slow motion, give me motivation. Breathe out now, and then on the rival. Round up around, spit out all over. Rhyme like a rolling stone, come in the crowd. Watch out the moon, that this too loud. This was this sound and bombs whole ground. Surround up, don't ease your pace, cause enemies brutal. Moment of truth, there ain't no truth. You're the only one world, one law. But the battle goes on, shadows all mass destruction.
Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down.
Battlegrounds right here. It's a man's world. Gotta get ready for this right here. Hey yo. Here's a wake, anger breathes out, face reality. Never be charity. The enemy, your buddy, covers all society. Damn right, mommy's not here, gonna fight all night. Right here, shadow 10 o'clock direction. Seize the moment, destroy the nation. You run slow motion, give me motivation. Breathe out now.
Oops. I was looking through the track list. Alright, so we're back. Let's talk about resonance structures over on the screen. No, Maya, oh my goodness. She came in and interrupted me no less than 4 times during the break, so now I'm just immediately going to spray bottle her. All right, so here are our structures for ozone. They are identical in the sense that I did the same thing to make them, but they don't actually look identical. If I was going to label these atoms as oxygen A, B, and C, and you can kind of label atoms in reality, you just have to have isotopes, right? So maybe oxygen A is one isotope, oxygen B is a different isotope, and oxygen C is a different still isotope. Then these structures would not be equivalent, right? Because one would have a double bond between A and B, and the other would have a double bond between B and C. And single bonds and double bonds aren't the same. So, how do we reconcile this fact that we can make symmetrical results that are mathematically equivalent, but like in reality, there should be something different here? Then how do we reconcile the fact that, like, why are there two pairs of electrons shared over on the left side, but only one over here? If they're all the same atom, shouldn't the bonds all be equal? But then that'd be like 1.5 bonds, right? And it turns out that this is where our models start to fall apart with describing molecules. Because the idea of having 1.5 bonds sounds really weird. But in reality, that's actually what happens, is we get the average of the structures that we've drawn here. So these models get us to the correct answer if we average them. And so what we call this choice of structure is called a resonance structure. And so a resonance structure is a pair of structures that at any point when you are constructing them, they differ only by electrons that have been shuffled around. So for example, to get from the structure on the left, let me clear the screen real quick here. To get from the structure on the left to the structure on the right, I could take this double bonded pair of electrons and put it back here, which would then break the octet on my central atom. So I need to replace it by putting this pair of electrons to go into this space, which would then fix it. So a resonance structure requires me to only move around electrons. So I cannot change connectivity. I can only increase the number of bonds above 1 or reduce it back down to 1 to make a resonance structure. If I can do this by shuffling around electrons, I have a resonance structure. Do I still have phosphate on the screen here? No, but I have SO3. So over here, if I go over back to SO3, we can say that the structures I was drawing for SO3, these are all resonance structures, because here I took this pair of electrons and just moved it into the middle. And then on this Lewis structure right here, I took this pair and put them in here. All I was doing to go from this structure to this structure was moving around electrons to change the number of bonds above 1. So these three would all be resonance structures. Now, in some cases, resonance structures are equivalent. So down here, these are equivalent because they're just mirror images of each other. Up here, these resonance structures are not equivalent, and there is a best resonance structure. Most of the time, with the problems that we're going to be doing, we're going to be working with resonance structure possibilities where they're equivalent. Now, how do you calculate the actual bond order for a structure that has resonance structures? And this is going to be why we're going to deal with equivalent structures, because it's just way easier to ask you questions like this. So if I go back here, I just erased ozone, but that's okay. I'm going to draw the Lewis structures for ozone really quickly. So there's one resonance structure. And there's the other resonance structure. This looks really bad. Let me try and fix this. There we go. Okay. So now what I'm going to do is I'm going to indicate a bond position in my molecule. I'm going to do that for both structures. I'm going to pick the same position in both. So I can either pick the left bond or the right bond. I'm going to just pick the left bond. So this is the bond I'm going to indicate. I'm going to indicate it in both structures. If I had multiple resonance structures, like 3 or 4 or more, I'd indicate that same bond in all those structures. And then what I'm going to do is I'm going to define what's called the bond order. The bond order is the actual number of bonds between these atoms. Oops. And what's going to be really cool here is that this can be a fraction. So I don't have to have a whole number of bonds. Okay, and so the bond order is going to be the following. It's going to be the number of bonds in this position divided by the number of structures. So let's count the number of bonds in this position. So we have to look at all the structures because those are all in that left position. So there are 3 bonds that are drawn here. Here's a double, and here's a single. I'm going to divide that by the number of structures. And that will be my bond order. So what that means is that in ozone, in the left position, the actual molecule of ozone, like the actual molecule you could like put in a bottle or put in the atmosphere to absorb UV, that actual ozone, would have a bond that would demonstrate the characteristics of something between a single bond and a double bond. And that our Lewis structure doesn't accurately predict that because we hit the limits of what our Lewis structure can do. Now, if you do the other side of the bond here, I'll pick a darker purple here, you would still get 3 halves. And so that shows us that, okay, both sides of the ozone central atom have equivalent bonds, and that makes sense given what we know about ozone. Like, they're all oxygen, right? The electrons should distribute roughly evenly over the surface of the molecule. And it turns out that when we look at resonance, we conclude that they do. We're going to look at other molecules that are very similar to this, like nitrate and nitrite, to discuss resonance structures. Now, if you draw resonance structures for your molecules, you got to draw a double-headed arrow between them. That double-headed arrow will indicate that, oh, the molecules you're looking at on my paper are resonance structures. They're equivalent. All right, so let's do nitrate here as our example. And we'll follow the same sort of rules that we just did. We'll try and describe the bonding. So if I draw the Lewis structure for nitrate, I get 5 electrons plus 3 times 6 electrons, and I get this extra electron. So I should have 24 electrons in my structure. So here we go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now, I don't have an octet with nitrogen, so I got to double bond something. So there's my structure, but could I have done it differently? I could totally have done it differently if I put the double bond in a different spot, right? I can't have both double bonds because I would break the octet of nitrogen, and I'm not a period 3 element. So nitrogen can have at most 8 electrons around it. So this would be a valid structure for nitrate. And so with this, I could put the double bond on this side if I wanted to instead. And because these are all ions, we got to do this. I drew through my structure. There we go. And then these are all Lewis or resonance structures, so we're going to put these arrow indicators there. Okay, cool. We've drawn the Lewis structure of nitrate, and we've discovered that it has 3 resonance structures because I could just move the double bond around, right? Any of those are equivalent. Now, what is the real structure? So let's choose a position. I'm going to pick the top position here. You could pick any position you want. And let's calculate the bond order. So the bond order, or if you want to be really stinky about it, you could call it the BO, would be 4 bonds, because I have 1, 2, 3, 4, over 3 structures. And so what that tells me is that the bond length between that oxygen and that nitrogen would be about what we would call a 4/3 bond. So it'd be a little bit closer to what a single bond is like than what a double bond is like. We haven't really talked about what double bonds are in terms of length and strength. Obviously, single bonds and double bonds, a double bond is probably stronger, and yeah, totally is because there's more electrons in there. A 4/3 bond would be stronger than a single bond, but it would be not quite as close as a double bond. I think at the very end of chapter 4, we're going to talk very briefly about bond energy and length. So that's what we do for resonance structures, is we draw as many possible equivalent structures as we can by only shuffling around electrons. So for example, here, I took these electrons, put them back up here, and then I moved these into its spot to get this structure. And I could do something similar for the one on the right. Oops, there's our picture right there. Now, I don't actually want you to do this example because what it turns out, if you do SO3, there are like 70,000 Lewis structures that you can draw. And then SO32 minus, you end up with only one possible structure. So we're not going to worry about that just yet. And also, we haven't talked about bond length, so don't worry about this just yet either. I am gonna do this example because I want to talk about benzene a little bit. So if you draw benzene, benzene is a very important organic compound. That looks like this. So let's draw benzene. So the first clue that I gave on there was the carbons form a 6-membered ring. That looks like this. And then I have 6 hydrogens available, so I'm going to just put 1 on each of these. And if you count the number of electrons in benzene, the result that you'll get is that there are 6 more electrons available, which means that you have to end up doing something like this. Now, could I have chosen a different option? Could I have put the 2 double bonds next to each other? Well, if I did this instead, that wouldn't work because now this carbon right here has 5 bonds. That would break the octet rule. So I'm sort of forced into specific orientations. But if I moved this one between these two, this one would get forced over here, and this one would get forced over here. And the result that I would get would be, I'm going to not draw the C's or H's on there this time. I would get this instead, right? Whereas before, I had this instead. And you may have seen this organic nomenclature before. You don't need to know how to do this until you get to 261. But what I've shown here is that I can move the double bonds around, and so these two are resonance structures of each other. In fact, when you have electrons that are resonance and all the bonds are together, what we end up doing is we put a dotted line through them in some illustrations, so you might see this. And the term that we call this is delocalized. Oops. Electrons. In other words, whenever you have a resonance structure, the electrons that you are shuffling around in all of those resonance structures are delocalized. They are just sort of roaming about on the average between all the bonds that have resonance structures between them. So if I wanted to look at which bonds were delocalized right here, my double bond would be delocalized across the entire structure. So those electrons in that double bond are actually everywhere, which is how you get the 1/3 of a bond extra. Because you have all the single bonds, and then you have that extra one bond distributed across all of the other atoms. And it's like that just because that's how many electrons the structure has, and we want to get the average. So resonance structures are this really cool thing that helps us explain why we get equivalent drawings in our Lewis structures. But the problem that resonance structures bring us is that up until now, Lewis structures have been pretty good to us. Like, we get a really close representation of a molecule, and then we apply this idea and concept, and it starts to all fall apart. And that is an unfortunate side effect of Lewis structures. It's a good model, but it's not going to be perfect. And at times we will have to modify it so that it works with what we know. All right, how much time do we have left? I got like 15, 20 minutes or so. So let's talk about geometry. I'm going to introduce you to geometry, but more importantly, what I'm going to introduce you to is, and I need to get the link for it. If it will load. This. So we're going to put this on the screen here. That's the chat. This is what I want. All right, this is Mol View. And what Mol View is it's going to help us out in trying to understand how structures work. So I'm just going to cover the screen here with this. So on the left here, let me hit the trash can here real quick. I'm going to draw a really simple molecule. So I'm going to draw the Lewis structure of... let's just do, I don't know, we'll do methane. There we go. I'm just going to randomly put my bonds around my molecule. So let's say I drew a Lewis structure. On Mol View, what you can do is you can push the button to tidy up your structure to make it look a little bit cleaner. But then what else you can do is you can render it in 3D. So what I'm going to do is I'm going to hit this button, and this 2D structure that we drew as a Lewis structure now looks like this over here, and I can then spin this around. This is what the molecule actually looks like in 3D. And you might notice, very interestingly, that instead of it being a cross or a plus or an X or whatever you want to call it, we get a shape that's very different, right? There's no X shape here, unless I hold it in this specific orientation. But then when I spin it in any way, you can see that it's definitely not all on the same plane. I have like a sort of pyramid thing going on here, right? And I can do this with any molecule I want to. So if I go... Oops, not that. If I draw, like, say, I don't know, something like this, with a bunch of carbons in it, and then maybe we got an O sticking out here, and there's an O over here. And we'll make these double bonds. And the rest is H's. So we'll go H, H, H. Oops. Oh, you know what? This is fine. Oops. So I could take really complex molecules and then throw them in the renderer. And so this is what I was doing. So first we'll tidy up. So that's what my structure looks like, and then we'll render it. And this is what it looks like in 3D. So that's really cool that we can do that. And you can just spin this around and look at it however you want to. This is going to be really useful for you in this section of the experiment because you're going to be asked to predict the actual geometry of a molecule. Now, whether you do that by building it in MolView or by writing it on paper and then looking at your structure and predicting from the structure, it doesn't really matter to me. I'm concerned that you get the terminology down and then understand that, like, oh, okay, when I say tetrahedral, what I mean is this part over here where I've got stuff pointing out in 4 different directions. And when I say trigonal planar, I mean something that's flat in that local region. I'm trying to make it look flat. There we go. So that's MolView, and you're going to want to play around with that as you look at the exercises in this section, or maybe even use it on your quiz. If it helps you to visualize, then great. When you get to organic chemistry, I would actually let you have a model kit. You could just build the models during the exam. Like, that's totally fair. Learning and thinking in 3D is really, really hard. So I would encourage you to actually use this. But do mind how much time that it takes to actually look up the structures and construct them. So we're actually going to care about the orientation of all of the atoms in 3 dimensions because those orientations will restrict other molecules from interacting with them in certain ways. For example, you can't have 2 molecules inhabit the same physical space, right? Because matter cannot pass through other matter. So if I have a molecule that is very, very large and round and makes like a spherical shape, other molecules can't go into that shape. However, if I have a molecule that's more like a donut, I could put things in the donut, or maybe if it's like a saddle, I guess you could put a molecule in the saddle. That's really important for enzymes. So when you get to biology, enzyme shape is very, very particular. You want only certain molecules to go in the enzyme to react. If you put the wrong molecule in there, you could die. That's how poisons affect us, is they clog up your enzymes, and then the enzymes don't function, and that enzyme happened to be the thing that carries all of your oxygen through your body, so then you're fucked, is basically what I was going to say. So geometry becomes super important, and so we're going to study it in great detail in here. So first thing that we're going to talk about for geometry is bond length. Bond length is typically measured in angstroms. An angstrom is 1 times 10 to the minus 10 of a meter. The other unit that's used frequently is picometers, and that's just 10 to the minus 12 meters. So up here, this length right here between this carbon and this oxygen is 121 picometers. So we care about that. And then the next thing that we're going to care about is the bond angle. The bond angle is the dimensional relationship between any 2 bonds. So I have the CH bond here and this CH bond here. The angle that is made right here is 118 degrees. Now, those numbers are not worth memorizing. There will be a set of numbers that I do want you to know. 118 is not one of them. And you should never memorize bond lengths. You can always look up a bond length. What we're going to do is predict lengths of bonds based on our structures. Now, in the previous section, we were talking about how we had bonds that had different strength associated with them. So, for example, a single bond versus a double bond versus a triple bond. Now, just in case it comes up later, I don't remember where the slide is where we talk about this, but let's talk about it now. So, I've arranged these in order of increasing strength. So bonds get stronger as you increase the number of electrons between them. But an interesting feature of this is that in doing that, I can't write in this orientation. I've ranked them in decreasing length. So length increases as the number of bonds decreases. So the triple bond is the strongest of these three, but it's also the shortest. Whereas the single bond is the weakest of these three bonds, but it is also the longest. And the double bond would be somewhere in between. The last thing I want to comment on is that this scale is nonlinear. So what that means is that a single bond is not half as strong as a double bond, and a triple bond is not 3 times as strong as a single bond. Likewise, the distance between these doesn't get halved. So a single bond is not twice as long as a double bond, which would be like 3 halves as long as a triple bond. So that's not what happens. The numbers that occur here are arbitrary, but the trends are followed. So bonds get stronger. They have a higher potential energy as you put more electrons between them, and their length gets smaller as you increase the number of bonds. But that's all we can tell. So a single bond might be like 1.5 angstroms, a double might be 1.2, and a triple might be 1.1, for example. It totally depends on what all the other bonds are around the atoms. So that's the sort of thing that we would just have to do an experiment with in order to calculate. Now, because all of the molecules that we will be working with in Lewis structures have a shape to them, like they exist in 3 dimensions, we could predict their shape using a very simple theory. And that theory involves valence electrons. What do all electrons do to each other? Well, valence electrons repel, and they typically exist in pairs, right? In a bond or a non-bonding pair, you would have 2 electrons. And so that's where you get VSEPR theory. VSEPR theory stands for valence shell, electron pair, repulsion. Now, obviously, it's probably pronounced VSEPR, but nobody says that because that's stupid. So, whenever I call it VSEPR, we're referring to geometry. So VSEPR theory is just, what is the shape of the molecule? It totally depends on how many electrons you have. Don't worry about the identity of the atoms, worry about the number of electrons. That's going to govern the shape. Now, the identity of the atoms and the shape can be related because oxygen, for example, brings 6 valence electrons. You're going to get a different shape than something that only brings 5. But if I'm comparing 2 things that have 6 valence electrons, like oxygen and sulfur, I could get similar results, and it turns out you do. So we're only going to care about the number of valence electrons when determining shape, and everything else is just going to fall into place after that. Now, when we draw our Lewis structure, we're going to have various things that are aligned around our atom that we're going to determine geometry. So this would be NO2 minus. Here's our Lewis structure. And around the central atom, I'm going to highlight the central atom here, so that's nitrogen. I would want to determine its geometry. And what I'm going to do is I'm going to take the highlighter in blue, and I'm going to highlight places where there are electrons around the central atom. So here are electrons. They are around the central atom. Here's a bond of electrons. And then here's a double bond of electrons. How many regions did I highlight in blue? It turns out I highlighted 3. These regions are called electron domains. An electron domain is very simply a place electrons exist around the atom, specifically the central atom. That should be a T. Oh my goodness. My handwriting on PowerPoint. I don't know what it is about PowerPoint. It like tries to guess where my pen stroke is, or it doesn't update as fast, I guess, or something. Now, as you can see, I did not distinguish between a single bond and a double bond. For a double bond, I just have more electrons between the 2 atoms. But they're still in this space between the atoms, so I indicate that as one electron domain. So, an electron domain can be a non-bonding pair of electrons or bonded electrons. Whether that is a single, double, or triple bond, we count these all as one electron domain. In each instance that you have. So if I had 2 double bonds coming out of the central atom, I would have 2 electron domains. If I had 4 single bonds, I would have 4 electron domains. All right. What does that mean for our classification? Damn it, your textbook changed this on me. So the previous textbook I taught out of it was electron domain. So apparently your textbook calls it an electron group. I call it an electron domain. Same thing. What does this mean in terms of our shape for our molecule? Well, if electrons repel, electron domains would also repel. So bonds would repel each other, non-bonding electron pairs would repel each other, and so on and so forth. The end result is that depending on the number of electron domains around your central atom, that's going to dictate a specific shape that you get. So we're going to just count electron domains whenever we draw the Lewis structure of something. And that's going to give us one of these possible shapes here. So you can either have 2 electron domains, 3, 4, 5, or 6 for this class. It goes past 6, but we're only going to do 6. So what I'm going to do is I'm going to give you this link, which lets you play with shapes on, I want to say this is like Colorado.edu. Yeah, Colorado.edu. So I'm going to put this link in the chat for you. And so this actually makes you download it because it's Java. But it should be able to work in your web browser if you're using Chrome. So when we go into this, make this a little bit bigger. Oh, no, I have everything on the screen. Okay. I'm going to click on model first because I'm just going to work with generic molecules here. So this is what this looks like. I did not capture everything. Okay. There we go. So I have some generic molecule here, and what I can do is I can drag this around. And you can see that the other bond that I have here is repelled by it. Hey, what's going on? Do you have that one friend that does this to you, and you're just like, go away? They're like, no, I'm over here. No, I'm over here. Ah. And so if I actually hit show bond angles, you could see that these two things would be related by a bond angle of 180 degrees because they could not physically get further apart, right? If I move this, that number changes, but then when I stop moving it, it equilibrates back to 180. So you can see that the electron domains, which are the bonds in this case, repel each other. Now I could replace one of those with an electron pair. I can't put a bond angle because there's not actually a bond here, but you could see that the same thing happens here. Or I could do this. And whether I have one electron pair or two, same thing. That looks a little vulgar, doesn't it? Now what I can do is I can just start putting things in here. Whoop, there we go. So now I have 3 things. Maybe one of them is a double bond. Who knows, right? We'll just do this. Because they're all electrons, they're going to repel each other apart the same distance. And the shape that I get looks like this. If I put a 4th thing in there, oops, there we go, like that. Now I suddenly enter into 3D. And you can see that the angles here, they aren't on a circle anymore. They're kind of in 3 dimensions here. And they're all 109.5. And then finally I can add 5, which gets me this, where I have different angles. So these are all 90, but when I look up here, they're 120. You could see that shape that I drew before if I can orient it in the right direction here. There we go. This is what I had on when I drew it on the PowerPoint, was something that looked like this. And if I put another one in there, then I have the square planar version of it too. So those are the basic 6 shapes that we're going to be looking at. We haven't talked about assigning them names yet. So all of these do have different names that you can see. And they match up with the names on the slide. But what we're going to do when we return for tomorrow's lecture is we're going to go over all of the different shapes and their names. And then we're going to talk about, well, okay, if I have the same shape, but I start replacing them with electron pairs, and we consider the fact that electron pairs are small, and thus you wouldn't be able to see them, what would happen to the overall shape? Would that change it? Well, for the shape that we're talking about today, no, but for the actual geometry of it that we're going to talk about later, it would. So this website's going to be really useful to you. You can also then go and play around with actual molecules. You can put in, they have several molecules in here that you can just play around with. You can look at their bond angles. You can look at their geometries. Here's water, for example. And just play around with this. So that's your exercise for tonight, is just goof around with both MolView and the molecular shapes generator at PHET. Because when we come back tomorrow for lecture, we're going to be using all of these. Okay? That's all I got. I hope everybody had a good weekend. Thanks for coming to the lecture. Sorry, I'm trying to delay while I'm getting the outro music up because I never remember. I mean, that's fine. I'll just waste your time. That's okay. There it is. All right, so have a wonderful rest of your evening. I hit play and you can't hear it because I have this muted. Have a wonderful rest of your evening. Make sure to look at those molecular shapes generators and then do quiz number 3. It's due tomorrow. See you for the last few lectures.